The next speaker is from Khalifa University, university in the UAE. His name is Mohamad Chehadeh. Please don't kill me if I'm not pronouncing it correctly. And his talk title is Real-Time System Identifications of Unmanned Aerial Vehicle Using Deep Neural Networks and the Modified Relay Feedback Test.
Yeah, thank you, Doctor. And thank you, Professor Antonio, for the nice presentation. Let me say good afternoon and good evening, depending on where you are. And this talk is about real-time system identification of unmanned aerial vehicles using deep neural networks and the modified relay feedback test. This is Mohamad Chehadeh speaking. I'm from Khalifa University. Khalifa University Center for, let me quickly just introduce from where we are coming. So Khalifa University Center for Autonomous Robotic Systems was established in 2011. It was formerly known as Khalifa University Robotics Institute. It focuses on autonomous vehicles and industrial applications. And currently in KU cars, there is 50 multidisciplinary researchers. We have multiple state-of-the-art research labs, and the KU cars research focus is on 3 themes. And the one that this presentation is concerned about is robotics for extreme environments. We have multiple state-of-the-art lab facilities here for robotics research that cover approximately 1,000 meters square across 2 campuses. So let me start with the main part of this talk. So, can we achieve identification of overall UAV dynamics in real time? Why we did have asked this question? Because if we can answer it, we would shorten development time, also reduce development cost as a result. And this makes applications that require high performance of UAVs widely accessible. So we have formulated the problem of identification as follows. So we have considered a planar video UAV family. So because we need to fix the model of our system, its structure, but still we assume that our system have unknown drag, delays, actuator dynamics, physical characteristics, configuration. So for example, if it's quad, hexa, or octocopter. However, we assume that we have known bounds, and these bounds can still be very wide. So for example, we are considering in our recent publications, UAVs that range in span, motor-to-motor span from a few centimeters to a few meters. Let me go here a bit technical and let me here have a gentle introduction into this field of online tuning. Sorry, this assumes some knowledge of control systems theory that's in the undergraduate level. So historically, we have what's called the relay feedback test. Relay feedback test was introduced in 1984. And with the relay feedback test, we can find the ultimate frequency and the ultimate amplitude of our system using a single test. So we inject a relay in our unknown system. So for example, we have here 4 unknown processes. And this is the Nyquist plot of these 4 processes. We get the steady state frequency and amplitude due to the relay excitation. And from that, we can know this point on the Nyquist curve. Later on, this idea was developed. Okay, what if we can identify different points on the Nyquist curve? And here the modified relay feedback test was introduced. So basically we have an additional degree of freedom compared to the relay feedback test. And this degree of freedom, we call it the phase of the test. So we can select it based on our family of unknown processes. This additional degree of freedom have introduced a challenge. So how we can select the phase of the test? We have used optimization under process uncertainty. So we have considered all the processes and in the range, admissible ranges of UAVs, and we have done Monte Carlo simulations to find what we call the distinguishing phase. And this is the result of this. So using a single test at the distinguishing phase, it's enough to achieve very accurate identification and tuning of controllers. So very fast adaptation can be done, almost optimal, if we have a single test at the distinguishing phase. From another perspective to the same problem, identification usually requires a lot of data. But here, we are having a very interesting characteristic of the system. We have data efficiency. So in just a single frequency of the system that's parameterized by a phase, if we know the frequency of the oscillation, amplitude of the oscillation, also the shape of the oscillation, because these relay tests are nonlinear. If we know them, we can map them back to what process have produced them. And therefore, we have the need for deep neural networks to provide this inverse map. So this is how it looks like in a computer simulation. So this is, for example, the model structure that we have considered for attitude control of UAVs. So we have 3 unknown lag parameters. We have the time delay, we have 2 time constants that we have considered. And if we consider this parameter space, we have did a sampling in this parameter space such that every point represents a process or a single UAV design. So we have hundreds of UAV designs in our domain, and we have produced the response of the system, MRFT response, in simulation. So, for example, here I show that different UAV designs have different shape of the oscillation. This is the recipe for this methodology. If we excite the UAV with unknown dynamics, we don't know what is the physical characteristics of this UAV. So we excite steady-state oscillations using MRFT at the distinguishing phase. So this is the unknown system. Then we take the controller output and the observed process variable to a data pre-processing and then to system identification to find what is the underlying process and what's the corresponding optimal controller. So all of this can happen in real time, and the stability and safety is guaranteed in the adaptation phase. So let me show you here some experimental results. So this was one of our early work. So in this work, we are concerned with the tuning of altitude loops and attitude loops because they share the same model structure. So the system here, let me go back to so we have excited the oscillations here. As you can see, the system was in operation, under operation of the relay. So we take a single steady state excitation, we pass it through the DNN, and we could know what is this UAV, what's its size, its characteristics. And accordingly, we have found the optimal PD controller. Just a single cycle that takes that has a period of less than half a second. So you can see that the system is robust to external nudges, even if the characteristics of the system change. We can repeat the test, do the tuning, And all of this can be run on real time. And we have optimal performance again. So the same adaptation now is applied to the attitude control loops. Adaptation done. And now we try to apply external disturbance, in this case, induced wind speed of 5 meters per second. And again, some external nudges. So in this early work that that I'm displaying here, we are not yet concerned with outer loop tuning. And because outer loop tuning or positional loop tunings, like for example, moving in translational axis, requires a different treatment. And why is that? Because we have a different parameter space that's quite big. So we have here, it would be in total 5 unknowns. So 2 time delays and 3 time constants. So we have developed an approach where we do identification and tuning in cascade. So for example, we do attitude identification. We find that this is the right process. This is the describing process of our dynamics. Then from that, we do another identification at a specified distinguishing phase for the translational dynamics. And we identify which process is the correct one, is the most describing one. The results of this can be quite remarkable. In this video, I show a UAV. So this UAV, prior to takeoff, doesn't know its own dynamics. It doesn't know, is it a 1 meter span UAV or a few centimeters? How big are the motors? What are the delays in the sensor system? So from takeoff, it starts shaking. It starts identifying its own parameters. So you see, it checks on all the channels and all the control channels through the self-excited MRFT oscillations. Yeah, so once tuning is done for every channel, now it's tuning the translational loops because it's done with tuning of the inner attitude loop. And now we show the control performance, the high performance of even these controllers has been achieved using fast adaptation, online adaptation, that lasts for less than 15 seconds overall. Doing a window passage here again, but at a speed that's really close to the minimum geometrically achievable speed. We have tested this algorithm on multiple sizes, on multiple configurations. So you can see that this identification method is very stable, despite the fact that the underlying UAV design is not known a priori. Another interesting feature that we got from these results is that the identification accuracy is quite high. So in this experiment, I just tried to show the simulation and experimentation match. So the UAV here tries to follow a figure of 8, reaching a speed of, in this case, slightly higher than 2 meters per second. And you can see the great match between the simulation and experimentation. So this opens the door for a few possible applications. So for example, because we have accurate knowledge of the model of the system, we can perform specific purpose tuning, like tuning for tracking, disturbance rejection, interaction, so on. And because of the high match between the simulation and experimentation, this serves as a stepping stone towards closing simulation to reality gap. Currently, we are working on the following. We are trying to extend the application of this algorithm, deep neural network, a modified relay feedback test, DNN MRFT, to visual servoing and SLAM problems. We are also exploring the use of identification results and estimation tasks. We are also addressing the nonlinearities through gain scheduling, where we can do the test at different operating modes of the UAV. And because the system description that we are getting is linear, we can, this opens the door also for lightweight planning algorithms. So thank you very much for listening, and hope you find it useful. And I don't know if I have time to answer questions.
Thank you, Mohamad. Yeah, we are a bit late, but maybe we have time for one question if there is anything from the audience. Otherwise, I can ask a very quick one. It's very interesting work, I think, with a lot of practical utility. I'm thinking, do you think it can be extended to vehicles with totally different dynamics, for example, like fixed wings UAVs? Is this approach, because they're actually much harder to tune than the quadrotor. So do you think it can be ported, the methodology can be ported to fixed wings UAV?
Yeah, I think that's quite fine. It's just a straightforward extension to fixed wings, because what we care about here is the model structure, and through the modified relay feedback test, we achieve the best possible linear description of the system. So we can do this test at different operating modes. For example, if the controller gains needs to be changed or scheduled based on the speed of the UAV or the maneuver that is undertaking right now.
So it would basically reduce the need of a skilled pilot. This pilot would be a little bit less skilled because the system will be doing more by itself, I guess.
In fact, the pilot is not needed to collect any data.
Okay.
So in this experiment where the UAV took off, it was all autonomous. So it should have zero intervention from the pilot.
Very useful. Thank you very much.